Hello guys, welcome to the Brains and Needles podcast. So today we are going to talk about DKA, Diabetic Ketoacidosis. So what is DKA or Diabetic Ketoacidosis? So it is a severe life-threatening complication in which the patient's body goes into ketogenesis, formation of ketone bodies. We'll come back to it. Now, what are the likely scenarios where a patient with diabetes might get into ketosis? So firstly, as the name is diabetic ketoacidosis, a patient is diabetic and under certain circumstances goes into ketosis. So what are the likely scenarios in which diabetic ketoacidosis can occur, or the person having diabetes can go under ketogenesis and further develop diabetic ketoacidotic coma? So firstly, the patient should have diabetes, type 1 or type 2. Most probable patient with these kind of complication will have type 1 diabetes, but in some cases even type 2 diabetes patient can develop DKA. So what are the factors or the scenarios under which one person or a patient's body can go into ketosis or ketogenesis, like formation of ketone bodies? So firstly, there might be a patient who's undiagnosed and only now presents with some of the symptoms of DKA, where the patient has never been under any test, doesn't know his sugar levels or any sort of thing. The second scenario where we know that the patient has diabetes or has gone under some test, after which the patient knows and is diagnosed with diabetes. Let's take in this case a patient is diagnosed with diabetes type 1. Henceforth, we'll just refer to the patient with diabetes type 1 because the probability of patient with diabetic type 1 getting DKA is more than diabetes type 2 patient. So the patient has diabetes, we have diagnosed it, but there can be scenarios in which there is compliance and non-compliance. So what is compliance? Compliance is like me as a doctor or endocrinologist gives a patient a certain dose of insulin to be taken, maybe short acting, long acting, anything, and the person follows it. That is compliance. A non-compliant patient may be a person who is not taking insulin on time, or is just forgetting to take insulin, or is just careless to not know how much units to be taken after eating food, or the regularity of it being taken. So there are two problems. So one with the compliance. So now you have given a certain amount of units of insulin to the patient follows it properly, no problem. But what can be the other factors which can, increase the amount of or increase the demand for insulin? So firstly, you should understand that in DKA, or specifically in diabetes in general, the patient in type 1 diabetes, the patient's beta cells of islet of Langerhans cannot produce insulin. So there is severe drop of insulin production or secretion in the patient. So the patient cannot produce insulin, so have to take insulin through synthetic insulin and so that the glucose in the body is utilized. So patient who's taking insulin under doctor's advice and still can develop DKA. So what are the probable causes? There are some scenarios in which the patient might be taking everything properly, but due to certain other factors, like if say a patient has some infection, let's say a respiratory infection, a sepsis, a gastrointestinal infection, that time insulin demand goes high because insulin is needed so that the glucose can go inside a cell or the peripheral tissue to go under its metabolism or further process of extracting energy of sorts. Second case can be a trauma, or let's say a patient is going under some surgery, some kind of infarction, most probable a myocardial infarction. There can be also, if you think about an mesenteric infarction. So these are the problems when a patient is compliant, but still the insulin demand increases due to this other factors which I mentioned. Now let's talk about the non-compliant patient, like the one which I mentioned. The patient is given X amount of units to be taken after meals, and calculate the bread units and take the insulin. So here certainly the patient is at fault because the patient isn't counting and is not careful enough to count the number of insulin units and the amount of bread units eaten or the carb he has consumed. So that is another problem which can exacerbate to cause a DKA. So now let's talk what happens when the insulin demand increases and certainly the patient is diabetic. So the insulin production or the secretion is very, like, the body is deficient of producing insulin. So what happens? There are contra regulatory hormones, or the hormones which are contra-insular, which when the insulin goes down, these hormones go up. Like for example, the first hormone being, if you look into the pancreatic cells, the alpha cells secrete glucagon, which inhibits insulin secretion. And from the central nervous system and the adrenal medulla, there can be epinephrine. The cortisol from the adrenal cortex is released, and the growth hormone is also released. So all the four hormones which I mentioned, the level goes up, and there is a ratio between insulin and the following hormones which I mentioned, the counter-regulatory hormones, which is disturbed. And due to this disturbance, there is some consequences. Now we'll see how each and every system is affected and how it leads to a vicious cycle leading to DKA and eventually can cause death or coma. So let's again go back and remember what I said. Your insulin level is down, so there are counter insular hormones like from the anterior pituitary growth hormone, the cortisol from the adrenal cortex, the epinephrine from the CNS and the adrenal medulla, and glucagon from the alpha cells of islet of Langerhans. So now there's a very funny situation because in the body insulin is low, and due to insulin is low, there is more circulating glucose in the blood. But when the insulin goes down, these hormones, they cause the or other systems in the body to increase the glucose into the blood, which is more, it is adding to the cause because already we have lot of glucose in the body which is not being utilized, and moreover these hormones are causing other systems to increase the amount of glucose. Why it is happening? Because the peripheral tissue is not getting glucose, which is sending the signal that there is no glucose. But actually there is glucose in the bloodstream. It's just that it is not being reached to the point where it should go. So therefore the body is fooled and the body starts producing glucose from different systems from the body. So firstly we should know that our body we need insulin so that the glucose can be utilized. But don't forget, like there's our scrotum. If there's scrotum and the brain, although we don't use it as much, the brain, but it's very well engineered. Even if there is no, like, it is not insulin dependent to get glucose for energy, and brain is one of the most important part of the body. So it is not insulin dependent, and even our scrotum, as you know the importance of it, so even it is not dependent on insulin to get glucose. So let's move to the subject we're talking about. So now what happens, liver is the main metabolizing organ, or all the metabolization mostly occurs in the liver. So what happens in the liver? So now let's move deeper in the liver. So there's no insulin. So what happens, there is glycogen storage in the liver. So the liver will use these glycogens and break it down and release glucose because the body is full. Again, the insulin is down, all these counter-insular hormones go up, they signal the body to release more glucose because peripheral tissue think that they don't have glucose. So now we're talking about the liver. So what happens in the liver? There is breakdown of gluconeolysis. So glycogenesis, or the breakdown of glycogen. So what happens? There is more glucose in the blood now. Second thing that happens is gluconeogenesis in the liver. What is it? Like, it is basically formation of glucose from non-carbohydrate source. So what are the non-carbohydrate source again? It can be amino acids, free fatty acids. We'll further look from where all these non-carbohydrate sources account to releasing of glucose from the liver into the bloodstream. Now, let's say what is the most relatable thing now you think about, like our muscles, right? Our muscles, they can produce glycogen, or the liver needs raw material, right? Like the non-carbohydrate source to cause gluconeogenesis. So now we can talk about the muscle. So what happens in the muscle? In the muscle, what happens? Like, for the liver to go under gluconeogenesis, we need raw material. So in the muscle, we have protein, which is then broken down into amino acids, which can then be utilized by the liver to go under gluconeogenesis. Another thing is, in the muscle, we also know there is something like glycogen, which is broken down and will eventually give liver raw materials. One thing to remember, in the muscle, the glycogen cannot be broken down to glucose directly. Of course, you need the liver to metabolize it. So the initial steps, like from the glycogen to the glucose 6-phosphate, the glycolysis occurs in the muscle, from glycogen to glucose 6-phosphate to lactate, and from the lactate then going to the liver, which is, if you remember from a biochemistry, it is known as the Cori cycle. So basically, it's breaking down of it is glycolysis in the muscle, and it up to the lactate, and then the lactate is used as a raw material to go under gluconeogenesis, which again increases the glucose. Another interesting being, let's say, what is the other source? Fatty acids, free fatty acids. The fatty acids need to come from a fat molecule, or adipose tissue. So in the adipose tissue, we have triglycerides. So triglycerides are broken down. Triglycerides are broken down by lipases, which break down the triglyceride. So triglycerides have one glycerol molecule and free fatty acids attached to it. So there is this lipoprotein lipase. They'll cause breakdown of these bonds, and glycerol and free fatty acid will go to the liver. In the liver, it will go into the mitochondria, and as it will be used as ketones. It will be used as ketones because these are glycerol and free fatty acids. I'll come back to it and go in further detail. So when it goes into mitochondria, and it will release ketone bodies. So what are ketone bodies? If you guys are in the third year onwards, you'll always think, whenever there's diabetic acidosis, even in the second year, you have always seen in the ketosis, if you look at the steps, you'll always see getting beta hydroxybutyric acid. But let me tell you, it is just a byproduct of the process of ketosis. It is not ketone body. Actual ketone bodies, so acetoacetate and acetone. These are the ketone bodies which are produced, and acetone being the most produced in most abundance. Always remember that the blood test or in the biochemistry, you'll always see beta hydroxybutyric acid, which is a byproduct of it. It is always present whenever, but the main ketone bodies are acetoacetate and acetone. So what happens further? Now the ketone bodies which are released, they are highly acidic. They release a lot of protons, and in our body there is maintenance of pH, so that it is not too acidic or not too alkaline. So due to this ketone body, there's a lot of acid being produced. And this triggers certain pumps in our body. I'll talk about it later. I'll come back to it, and because we need to know what happens in the initial stages when the patient goes under diabetic ketoacidosis. Second thing being is naturally being the bicarbonates, which will counter the acidic substance. So the bicarbonate which is present in the body, it will try to compensate. What happens when the acid is very high and our body has bicarbonates? Naturally, the chemicals will try to go under a reaction. So what will happen? This acids being H protons will react with the bicarbonate CO3 and will form carbonic acid, which will then dissociate into carbon dioxide and water. Now let me ask you something. If you're already done with the clinical part, or if you have some general knowledge, or you've just heard, you always listen about Kussmaul's breathing, about patient having these different type of breathing, this very characteristic to a diabetic ketoacidosis. So why it happens? Now let's jump back to the place where we stopped. So when this reaction occurs, what is produced? Carbonic acid, because H we have one proton. We just take a single event, so we have one proton plus HCO3. They'll mix H2CO3, which is carbonic acid, and then they'll dissociate into carbon dioxide, and the water will naturally go into the kidneys and will be excreted. But what happens? This carbon dioxide goes into the lungs, and carbon dioxide is produced in abundance. What happens? The CNS is triggered, and it tells the lung to basically it causes deep breathing. So the patient inspires deeply, like this. So and firstly there's tachypnea, because initially there's tachypnea. The patient's breathing rate is very high. And also the patient tries to fill in the full tidal volume, so patient develops Kussmaul's breathing due to this mechanism. During Kussmaul's breathing, what happens? What are the byproducts or the products of ketone body? What are the ketone body? In abundance, acetone is produced. So even in the breath you can smell acetone. You have a sweet smell, and you can smell it from a distance as well. While Kussmaul's breathing, the patient will have deep tachypnea, breathing with sweet smell of acetone. So now let's move to the kidney. So what will happen? There's more amount of glucose in the blood, so eventually it has to get excreted. So in the urine we have glucosuria, and also that due to lots of ketone bodies present in the blood, there will be ketonuria as well. Now let's jump to the point where I told you when the acid increases, there are certain pumps, which is the first point, and the second I mentioned the bicarbonates. So these pumps are known as potassium pumps. What are these? So whenever there is increase of acids, so what will happen? Whenever there is increase of acid, the potassium from these pumps are given out. There is loss of potassium. So initially when the patient comes with high potassium in the blood, and which eventually will be lost in the urine. So initially the patient might have hyperkalemia, and then after that there's increased loss of potassium, which also I'll talk about in the kidney. Also it is precipitated how more potassium is lost in the kidney. Now let's jump back to the kidney. The kidney will have glucosuria due to the more amount of glucose in the blood. Then ketonuria, but natural, it is due to the ketone bodies. Then you'll have kaliuria, which is potassium being deposited in the kidneys from the blood. What happens usually when glucose is from the Bowman's capsule, it is filtered down. Usually in the proximal convoluted tubule, this glucose is absorbed back into the blood, because there is so the amount of glucose is so high in the blood, it has not been absorbed, it has been excreted. As even if we have extra money, we just want to flex and spend all of it when you have extra. So same way the body also tries to extract the glucose. So along the way, what happens when there's so much amount of glucose, due to osmosis, or like osmotically, it also takes in more water from these from in the nephrons, and more number of water molecules are drawn in the excretion process. So when more number of water is drawn, what do you think? Imagine the Amazon river. It has a water which is a very high force. So eventually anything and everything inside coming in contact with it will also move inside the river. Same way, when the glucose is taking so much water molecules, there's turbulence, and due to this turbulence, other molecules are also lost in the also lost along with all the minerals, also lost along with glucose in the urine. Then can be phosphate, urea, and other minerals can also be lost. Now when we come to the distal convoluted tubule, there is some in the distal convoluted tubule, there is also loss of potassium from the distal convoluted tubule into the urine, which precipitates the caliuria, which I mentioned. So this again precipitates it. Forgot the most important part, GIT. So what happens? You're already losing so much water. You are dehydrated. So what you'll do? There'll be increased thirst. There will be increased thirst, and there'll be polydipsia. You want more water to drink, and your mouth will be dry. There'll be polydipsia. There will be loss of weight due to dehydration. So let's now have a summary. So what happens? Insulin is low. So all the hormones, if you want to repeat it or write it down, if you remember, you can write it down if you remember what I said. So I'll mention it again. Growth hormone from the anterior pituitary, cortisols from the cortex of adrenal, from the medulla and the CNS, epinephrine, and glucagon from the alpha cells. So these hormones, what will cause? It will cause systemic changes. So in the muscle, it will go under glycolysis, which is formation from glycogen to glucose 6-phosphate to lactate. And there is a Cori cycle when it goes to the liver, which gives it raw material to go into gluconeogenesis. And for gluconeogenesis in the liver, we need more raw material, we need non-carbohydrate source. So the second thing is amino acid. Again, protein in the muscle is broken down and it goes to the liver. And another source from where it can come is fatty acids. So in the adipose tissue, there are complex of free fatty acids and reserves in triglycerides. So it is broken down by lipase. It is broken down by the lipase to lipoprotein lipase, which breaks it down, and free fatty acid glycerol is sent to the mitochondria of the liver, which forms ketone bodies. I'll repeat the ketone bodies again. Main ketone bodies are acetone and acetic acid. Beta hydroxybutyric acid is only the byproduct. So, and what is the main one of the main characteristics comes up with due to the acid, reacts with the bicarbonates, forms carbonic acid, CO2H2, CO2 goes, tell the CNS to increase the tidal volume, increase deep respiration, tachypnea, and you have sweet smell due to acetone, Kussmaul's breathing. Come to the kidneys, glucose is flushed down, takes more water with it, potassium is lost from the potassium pumps, also from the distal convoluted tubules. Also, phosphate, urea, and other minerals are lost due to the turbulence caused by the amount of glucose and water being flushed out, and which is also called polyuria because of the frequent urination. Also, we have polydipsia because there's increased thirst, dehydrated state. So these all, and the CNS I mentioned, the Kussmaul breathing, and the lungs also covered under it. So now let's create a patient. So when a patient comes to you, let's say the patient will have blood glucose of more than 250, pH might be less than 7.3, bicarbonate, the normal level is 25 to 29 mega equivalent, but let's say in this case it's less than 15, and ketone is more than 5 millimole per liter. So this is the patient. So how do we treat the patient? Like 3 main steps. So you give fluid replacement. Oh no, okay, let's put it like that. You give insulin, you bring down the glucose level down, then you give fluid to the counter the dehydration, and then you give potassium. Is this the right order? No, this isn't the right order. So the right order will be firstly giving fluid replacement, then giving insulin therapy, which is controlled insulin therapy. All insulin is not pushed at once, because whenever, as I mentioned, when the insulin is given, it causes potassium to go down. The patient can die of arrhythmia or cardiac arrest. So remember, first fluid replacement, insulin, and after that we bring the potassium to the base value. So you should remember, always remember, the potassium should be like maybe more than that. The potassium is brought to the base level. Because never give a patient will say, okay, patient has diabetic ketoacidosis, his sugar is 250, I'll just give insulin, bring down the sugar, I've treated the patient. No, you kill the patient due to hypokalemia, which will cause arrhythmia and cardiac arrest. So remember, first fluid replacement, then you give your insulin, and then potassium therapy. Remember potassium IV. Remember you have to give insulin in a controlled manner. So let's talk about the whole scenario. The patient comes to you. So firstly, we need to do a thorough history and examination. This is being taught to you since the third year. How important is the anamnesis, the history of the patient to diagnose the patient. Second thing, we have to do, the first thing when the patient comes is ABC, airway, breathing and circulation. So you check the airway, is the patient breathing properly, the respiratory rate, the type of breathing. In the type of breathing you can find the close-mouth breathing, tachypnea and the sweet smell. In circulation we should have IV access, because in the hospital as soon as the patient give an IV, we start with the fluid replacement. So no, and also we take blood for investigation. Administer IV fluids like saline and administer insulin slowly. In the investigation, we'll do air blood gases to see what's going on. I've mentioned the pathophysiology of it. You do a total blood count so that you should also rule out infections or any you should also do blood biochemistry, because I said infections, infarcts can cause the amount of insulin to rise. Also, you should do an ECG to, if the patient is lost a lot of potassium, can go into, can have can have arrhythmias, or that sort of thing. And you should do urine analysis for the things I mentioned: caluria, polyuria, glucosuria, because lots of leukocytes are also given out. Ketonuria and phosphaturia should be taken. You should monitor pH using air blood gases. So always remember, during when the insulin is very low and all these hormones acting, the leukocytes are increased in the blood. So there might be some instances where the patient is infected, but the patient will have hypothermia. In diabetic ketoacidosis, the patient goes under hypothermia. So if you look at the patient, you will see the patient is normal, the temperature is normal, but still the infection might persist. So you should look for the blood for the infection. In some cases, the patient might be absolutely normal, but still the leukocytes may rise. So, a smart doctor should know that the patient can be in hypothermia and not show on when you measure the temperature, not show on the thermometer that the patient is having fever. So you should check for the blood for that. We use monitor, pH, ABGs, urine analysis, ECGs, and blood cultures, maybe if you want for the infection or have a previous history of some sorts. So that's all for today. Remember, if you sit down for this podcast you're listening, have a pen or a paper to jot down some points, so it will be better for you to remember the next time. Always you can listen to the podcast again, but jot down with a pen or a pencil so you remember this stuff. And again, subscribe to our Brains and Needle channel on Instagram and Facebook and YouTube as well. You can subscribe and share it. Please share with your fellow friends. I just want it to reach as many students as it can, because I really want my fellow mates to understand it in a understand these subjects in simpler words in an interesting way, be in a podcast. Thank you. That's all for today.